Hello friends, I'm back with the new part of this tutorial. So let's move on and talk about the next section, which is on how do transformer works. So in this article they have mentioned a bit of the transformer history. So history of the transformer, it's dragged back from June 2018, when for the first time GPT was introduced as the first transformer model. GPT is from OpenAI, as we all know that, and it's full from a generative pre-trained transformer, which means it will allow for the generation of the text, and it is pre-trained on the large number of data set or the corpus, and it is using transformer as an architecture, so it is named as GPT. And it is used for fine-tuning on various NLP tasks and obtain the state-of-art results. And in 2018 we have another transformer model called BOT, which is bi-directional encoder representation from transformers, and it is designed to produce better summaries of the sentence. We'll talk about this more in the next chapter. And then we have GPT-2 on February 2019, which is of course the bigger and more improved version of GPT, but due to some ethical concern it is not released publicly. And in 2019 October, DistillBot, which is the distill version or smaller version of the bot, which is 60% faster as well as 40% lighter in comparison to bot, was released, and it still retains 97% of bot's performance. That is the big thing. In October 2019, in the same month, BART and T5, two large pre-trained models were introduced. And in May 2020, GPT-3, which is even the bigger version of GPT-2, was introduced. It works well. GPT-3 works well without need for fine-tuning in a large variety of tasks, and it is publicly available as well. Various categories of transformer can be divided broadly into three groups, which are GPT-like, which means autoregressive model. Autoregressive models are mainly there which provide the output or help in text generation. And in the same way, next model is auto-encoding transformer models. The main focus of such kind of model is to learn from the input text, so that they will have a clear picture of the input text. And then last one is sequence-to-sequence transfer model. It is of course the combination of both encoder and decoder model, and it will help us to translate. Main purpose is for translating from one language to other, and many other things as well. We will talk about those things in detail later on. Let's move on to the next part. Here they are talking about transformers as a language model. All the transformer mentioned above, that is GPT, BOT, BART, T5 and so on, they have been trained as language models. This means they have been trained on large amount of raw text in self-supervised fashion. So the meaning of self-supervised is that they are trained on the large corpus of the data, and they don't need any kind of human intervention to label that data. The main purpose of those model is to develop statistical understanding of the language it was trained on, and later those general pre-trained model can be used for any particular task through the process of transfer learning, and then fine-tuning them in a supervised way through the human intervention. An example of the task is predicting the next word in a sentence, which is called as causal language modeling. because the output depends on the past and present inputs but not the future one. So we will, when we give it as a output input my, it will predict name, and these two, now my followed by the current output, will be given as an input again. So future output it will be predicted, and so on. So in this way we can predict or generate the sentence. Another example is that they are used as a Marx language modeling, as we have already done example in our previous section. So we can provide a sentence followed by randomly marked word, and the task of the model will be to predict the word in that marked place. Transformers are growing very rapidly. Now the number of the parameters are reaching up to the trillions level. So they are rising very rapidly. And this is the graph that shows how the different model has evolved in terms of the parameters. And the important thing is here, which is mentioned, is regarding CO2 emission. That's of course as the number of parameters are increasing, as well as the energy or resources required to train those models are also increasing, as a result of which carbon emission is also increased due to the fact that they contain a large number of parameters. As we can see in this chart again, CO2 emission for variety of human activities, and the state of art LM large language modeling, it should be LLM training, big science workshop including experiment, approximately 200 billion parameters produce the CO2 emission of 75,200 kg. So that's the very large number. Now what we can do, what we can contribute so that this kind of problem can be minimized. So the best thing is to do is to reuse the model. I mean, instead of training the whole model from the scratch, what we can do is we can use the pre-trained large model and fine-tune them on our research tasks or on our particular tasks. In this way, what we can do, we can reduce some carbon footprint. So if we want to do any kind of project, so what we can do, we can pick one suitable pre-trained model and start on fine-tuning that model. And the thing that mentioned it here is we can check how much our model is impacting or generating the carbon emission. Though there are many other links, let's look one of them. Let's see how it works. So yeah, compute your ML carbon impact. Let's go. Okay, so here is hardware type. Maybe we can select any, let's suppose, and how many hours we use for training. Let's suppose 100 hours, it's okay. And then we need to select the provider. Okay, let's leave it as it is. Yeah, so you can select your location. Let's select Asia, compute. Okay, so here is carbon emitted amount and carbon already offset by provider. So this is the thing, and you can go in details as well. So how this is generated, how much energy is required, and how much carbon emission is there. So you can go through this in detail. There are other things as well, like there is blog post regarding this whole total carbon emission through language modeling. You can go through them, but I won't be digging in those topics in detail as they are not so relevant. What we can contribute from our side is that wherever possible, let's try to use the pre-trained language model which are available and then fine-tune them into our own tasks. That will be the only thing we can do. Yes, so here is an example. We have a base model. We have a very large corpus of the data from where from where we will train this base model, and we need to invest a lot of money as well as time, and then we will have pre-trained language model. So now, instead of starting all the experiment again and again from base model, what we can do to control the carbon emission footprint, we can start working from the pre-trained language model. And yeah, that training can be done in a single CPU, as it don't require large corpus of the data, as it is already pre-trained, and it will require less amount of money, easily reproducible, as well as it will take less time, and then we will have our one fine-tuned model. As all the pre-trained model will have statistical representation of the language, so it's not worthy to retrain the same thing again and again. So it makes sense fine-tuning them on our one task. Here is one example. So if we have any fine-tuned pre-trained language model, we can fine-tune it on, let's suppose, ARCGIS corpus, which is all related to research paper, and we will have our one science research based model. The fine-tuning will only require a little amount of data. The knowledge pre-trained model has acquired is transferred, and hence it is called as a transfer learning. So statistical representation which is there in the pre-trained language model will be used by our fine-tuned language model. So that will save a lot of things. Let's dive deeper into the general architecture. So mainly the transfer model contains two blocks. One is encoder and another one is decoder. As you can clearly see in the figure, encoder receives inputs and build the representation of the data. That is, it will build the features. And the decoder part will also receive the inputs, and then one of the input is from the encoder part. The main purpose of this decoder is to generate the target sequences. And those target sequences will be again used to generate the next target sequences, and so on. So decoder is auto-generative. Each of this model, the transfer model, can be again divided into three types, which are encoder only models, decoder only models, and both combined model, that is encoder decoder model. They are also called as sequence to sequence model. The main task for encoder only models is in the scenario like sentence classification and named entity recognition, where the good understanding of the input is required. And decoder only models are used in the areas such as text generation, where the generative task is given more priority. And encoder decoder models or architecture are good in the generative tasks as well, in the scenario like translation or summarization, where we have to whole understand the things and then translate the content into another type. And then important concept in encoder or decoder is the attention layer. In old classical NLP models, what we did was that we give equal priority to all the tokens or the words in the sentences, and as a result of which we are stagnant towards the further progress. And one paper attention is all you need, change everything, as it introduced the concept of attention. And the concept is very simple. Let's go through it. So let's this is the site. I will share the link with you. It is the very good post that mention in detail about what is attention and how it works. I will just give you the overview of this part. So let's take one simple example over here. So let's suppose we have a sentence, she is eating a green apple. In old classical NLP thing, all the tokens or all the words are given equal priority. But we as a human beings, when we read this sentence, she is eating a green apple. So we create an image that eating is related to apple. We don't think that this word can be related to green or she is. In the same way, this concept of attention is used in the transformer model and it changed everything. Now we create our attention map. What we did is we create the attention map for individual words and try to relate which word the current word is paying more attention, and those two words will be highly related. Let's go through another example. Here is the one. For example, this is the sentence: the FBI is chasing a criminal on the run. When we are on the, attention is nowhere. When we move on to the next word, FBI, the whole attention is on the. We are moving on. As we are moving on, attention is being shifted. When we are in criminal, attention is on it, and so on. So when we are moving, the attention is also shifting. So in this way, attention in a sentence of a word can be manipulated, which is very helpful concept for further advancement in natural language processing. So this is this whole detail was first introduced in this paper. If you want to dig deeper into the topic of attention, you can go through this research paper as well. Yeah, and this attention is mentioned to introduce the transformer architecture. This is the first time this attention mechanism is mentioned, and they name their architecture the transformer architecture. So for the first time they introduce this concept as well as transformer architecture. The main use of this architecture was for the translation model. They use the transformer architecture for translation purpose. Let's go in detail about the architecture that they mention in their paper. The architecture that they mention in their paper is here. I will go through this architecture briefly as it has a lot of things and it will be difficult to cover all those things here. So let's look at the internal things. So we have encoder path, and in encoder we have inputs, and these are the embeddings of the inputs. As we all know that computers don't understand the words, so embedding is the way to represent the words into vector form or in terms of a number, so that it can be easily manipulated by the model. And then these embeddings can be of different types. Can be token embeddings, which represent the token into vectorial form, or it can be positional embeddings that will represent the position of a word in a sentence, and so on. After the embeddings things, it will be passed into multi-head attention. Now we have talked about the attention, and the concept of multi-head attention is that we will have not just single attention head but multiple attention head, so we can understand the context of the words in detail, so that we can explore some inner attention or inner things that we are missing with the single head attention mechanism. And then while passing the embeddings into the multi-head attention, next layer is the addition layer that will add all the things, followed by the normalization, and then we have feed forward layer for exploring further and processing the things, and again it will be followed by addition and normalization layer. Now this decoder part, we have inputs, and again we have embeddings which are passed to the masked multi-head attention. Now here the different thing is masked. we need to understand it. Suppose we are performing the translation. So here we have one sentence in one language and same sentence in another language that we are going to give input to our model. If we give whole sentence to our model, whole tokens of the sentence as an input to the decoder, it will able to glance into the future and it can easily generate the world. So it will be a kind of cheating like thing. So here Mark's multi-head attention perform the things of hiding the tokens which are from the future. They will only present the tokens, current tokens and all the past tokens to the model, hiding or masking all the future tokens so that our model won't be able to pick into the future tokens. And then again the output of the encoder and from the Mark's multi-head attention is passed into the multi-head attention layer, and it is then passed into the add and normalization followed by feed forward, add and normalization, and finally linear layer followed by softmax activation function. And then we have output probabilities of all the tokens. Now those tokens are passed back into the decoder and next level of tokens are generated. In this way this whole architecture works. If you want to dig deeper into it, you can go through the paper of the transformer and have a detailed knowledge about it. Okay, so after going through this one, I want to go back to the content. So this is all about the architecture. Now we have some terms like architecture, checkpoints and models. They are a little bit confusing and little bit similar. Let's dissect them. So architecture is the skeletal of the model. What does it mean? It is the definition of each layer and each operation that happens within the model. And checkpoint are just the weights which will be loaded into the given architecture. So architecture is a skeletal of the framework. Checkpoints are the weights that will be loaded into the given architecture so that it will start manipulating the tokens. And model is an umbrella word which is interchangeably used for both architecture and the checkpoint. And in this course they have avoided this term wherever possible and use architecture and checkpoints. Here is one example. For example, BOT is an architecture, while BOT based case is a set of weight trained by Google team for the first release of BOT is a checkpoint. So BOT case based case is a checkpoint, whereas BOT is an architecture. So this is all the things in this. Let's move on to the next part, which is related to encoder models. Let's talk about it. Encoder models, as we have already discussed, they have only encoder part of the transformer, or they have only encoder things. At each stage the attention layer can access all the words, as there is no masking. Masking is only present in the decoder part, so it has access to all the words in the sentence, and they are characterized as bidirectional attention and also called as auto encoding. So bidirectional attention means from left to right or right to left they can create the attention, and they are also called as auto encoding model. The transform model that have only encoders are termed as auto encoding as well. The pre-training of these models usually involves somehow corrupting the given sentence by masking the random word in it and asking the model to find or reconstruct the initial sentence. So the training things is done through masking of the words. Encoder models are this type of models are best suited for requiring understanding of the full sentence, as they have the whole context, and they are mainly used in the tasks like sentence classification and named entity recognition. also as well as extracting the answer from the given context. The various models that are under this family are listed here. If you want to dig dive, you can open it and then have a detailed understanding of those architecture along with their paper. So if you want to dive in deep, you can have a look onto those models as well. And then next we have decoder models. So as the name suggests, they only have decoder part of the transformer, and at each stage for a given word, attention layer can only access the word positioned before in the sentence. What we did is that we avoid the model to look into the future words by masking them, and those models are called auto-regressive model, and they generate the new words or the tokens depending upon the previous tokens. The pre-training of decoder model usually involves around predicting the next word in a sentence with the help of all the previous words given. These models are best suited for the tasks like text generation, and some of the examples are included over here. You can go through them whenever you have time. I will be moving on to the next topic. So final model or transform model is sequence to sequence model. So they have both encoder and decoder architecture in there. At each stage, the attention layer of encoder can access all the words. As we know, encoder can access all the words, and it will pass that towards the decoder, where decoder can only access the word which are positioned before the given input. The pre-training of this model can be done using the objective of encoder or decoder. No matter what kind of objective you want, you can use either the objective of encoder or the decoder, but sometimes they have their one complex kind of training weight. For instance, let's talk about the training of the T5. So T5 is pre-trained by replacing random span of text with a single marks special word. So random span of text, maybe 2, 3 or 4, 5 with a single marks special word, and the objective will be to predict the text that this word, marks word, will replace. They are mainly suitable for the tasks revolving around generating new sentence depending on the given input. The tasks can be like summarization, translation, or generative question answering. The various models under these topics are listed here. Let's go on to the final topic, which is related to bias and limitation. Yes, so now the question comes. As we are using the pre-trained model, all the problem or the biases that are present in the pre-trained model will also be introduced into our model. So let's go through examples how these biases are introduced. Let's open the file. Let's go. Let's install it, run anyway. And then let's talk about the bias. The main thing is that as we are using the pre-trained model, the pre-trained model can be not, it is trained on the various data, and all the data are from the different sources. So it can contain maybe some kind of wrong information, negative information, and all those information which are statistically in the memory or the weights of the pre-trained model are passed into our one model. And when we try to use our one model for various tasks, we can get biasness in our result. Let's go through one example. Let's suppose we are trying to predict the masked word. So this man works as a mask. So we are asking for the various jobs that a man can do, and in the same way various jobs a woman can do. Let's run through this model and let's try to find the result in the real time. I mean, the results are already mentioned, but let's do it again. Let's see how it runs. And it's loading. Okay, so here are the results. So the work which are related to man are listed as carpenter, followed by lawyer, farmer, businessman, and doctor. And the work related with women are nurse, maid, teacher, waitress, or we see the job prostitute here. So which is a kind of biasness. And we cannot correct this biasness as it has arrived from the pre-trained models. Let's try to see how it behaves for other people, like this man. Let's this, okay, let's try for some other content. This Asian man. Let's see how it discriminate or bias the things now. Let's have a look at it. Now, if we change the man to Asian, what we get is that first is followed by businessman, then it followed by tailor, merchant, doctor, teacher. So it's general thing, no, not any kind of biases it's in. But look at it. In general, when we pass women, the prostitute was the fifth one, and now we can see that it has rised up, and now it's in the second place. So yeah, so this is all the biases that is introduced into the pre-trained language model, and we don't have any way to deal with such kind of things, but we have to be careful while dealing with those kind of things. Let's get back to our topic. Okay, so yeah, so this is the summary of the chapter. So here we, in this whole chapter 1, we talked about the pipeline function, different kind of architecture, and which are encoder, decoder, and so on. The main task for encoder was sentence classification, named entity recognition, extractive question answering. We have used all those things, and the function of the decoder architecture was for text generation, and for encoder decoder they are used for summarization, translation, and generative question answering. So at the end of this chapter we have quiz. Let's try to go through the quiz as well. Let's have a look. Explore, the first question is explore the hub and look for Robota MLI, Robota large MNLI checkpoint. What does it perform? So let's copy it. I'm not sure what does it perform, so let's check for the model. Let's see. Robota. So here is the description. Let's directly go into the code. I think it's related to classification. Yeah, classification, classifier. Let's go back. So we have text classification. Let's go and submit. Okay, now what will the following code return? Yes, it's related to what? Name entity recognition. So it will return person, organization, and location. It's done. What should replace? So what should be here? As we will introduce the mask, it's for filling the mask. So yeah, mask is given in big bracket, not this one. So this will be the answer. Why this code fails? Yes, as we know that for in case of zero shot classification we have to provide our one label. So this label is not provided here. So that is the problem. Pipeline requires that labels be given to classify this text. Pipeline requires several sentences broken. The pipeline requires longer. No. So this is the one. What does transfer learning means? Transferring the knowledge of pre-trained model into the new model by training it on the same data set? No. Transferring the knowledge of pre-trained model to a new model by initializing the second model with the first model weights? It seems to be correct. Transferring the knowledge of pre-trained model to a new model by building the second model? No. So it's all about transferring the weight from the pre-trained model into our one model. true or false. Let's go through it. True or false? A language model usually does not need labels for its pre-training. Yes, as we all know that they work by self-supervision process, so they does not need labels. Let's go on the next part. Select the sentence that best describes the term model, architecture, and weights. Let's go through them. If a model is a building, its architecture is the blueprint, and the weight are the people living inside it. If a model is a building, architecture is its blueprint. The weights are not the people. This seems to be a little bit doubtful. Let's try other. An architecture is a map to build a model, and its weights are the cities represented on the map. Architecture is a succession of mathematical functions to build the model. Yes, they are functions, and weights are those function parameters. Yeah, so this sentence seems to be good fitted. Which of these models would you use for completing the prompts with generated text? For generating text, we have used decoder model, as encoder model is for classification tasks, and sequence is mainly used for summarization. So for the text generation, we will go with the decoder model. And now, which of those types of models you use for summarizing text? For text summarization, sequence to sequence model is the best one. And which of these models would you use for classification of the text? For the classification part, encoder model is the best one. It's suitable one, I mean. What possible source can the bias observed in a model have? A model is a fine-tuned version of the pre-trained model, and it picked up its bias from it. Yeah, this is the thing. The data the model was trained on is bias. The metric model was obtained on. So we obtained the bias from the pre-trained one. There's more. Oh, data could also contain the bias. That's maybe the things. Yeah, so this is all about the thing, all about this chapter. So I will be back with the new topics using transformer in my next part of the video. See you soon. Have a good day. Bye bye.